So far in this module, we've learned what a sequence is, how to represent sequences using closed formulas and recursive definitions, and how to use sigma and pi notation to find partial sums and products of sequences. In this video, we're going to examine two special types of sequences that have some distinctive behaviors. Take a look at this visual pattern, and let's see if we can count the number of stars at each stage. Let S sub n be the number of stars in the figure at stage n. If we start the indexing at 1, then S1 is 3, S2 is 5, and S3 is 7. I bet you can probably guess what the next several terms of the sequence are going to be without either a closed formula or a recursive definition. It's a safe guess that S4 will be 9, then S5 is 11, and so on, because all we're doing to get from one stage to the next is taking the current stage and adding 2. We can say in this case that the sequence is increasing by a constant amount, namely 2, each time I go from one stage to the next. A sequence with this kind of behavior, where the terms in the sequence change by a constant amount every time we go from one term to the next, is called an arithmetic sequence. So this is an arithmetic sequence, and here's another. The first sequence is arithmetic because the terms increase by a constant amount of 2 each time. The second one is also considered arithmetic, even though the terms are decreasing, because they are still changing by a constant amount, this time dropping by 3 each time. But this sequence is not arithmetic, because the difference between the first and second terms is 3, but the difference between the second and third terms is 6. Since that's not the same amount each time, this is not an arithmetic sequence. Arithmetic sequences increase or decrease like a staircase would, always moving up or down by the same height each time we take a step. Coming up with closed formulas and recursive definitions for arithmetic sequences is fairly easy. To get a closed formula for our star sequence, for example, we can use some concepts from basic algebra. If you think of a sequence as a function, which is what we do when we make a closed formula for it, then what you might notice about this function is that it increases at a constant rate, always up 2 for every increase of 1 in the input. Functions that behave like that are called linear functions. Linear functions are completely defined by their slope, which is the rate at which they change, and a point on the graph of the function. Well, the slope here is 2 because every increase of 1 in the input produces a change of 2 in the output. And I can look at the data here and see that the point 1, 3 would be on the graph of this function. So using what we called the point-slope form for the equation of a line back in algebra, we can write y minus y1 equals m times x minus x1, or y minus 3 equals 2 times x minus 1. That simplifies to y equals 2x plus 1, so the closed formula is a sub n equals 2n plus 1. Using a little Python to check shows me that this seems to be right. A recursive definition is even easier because we don't need any algebra. Just first of all realize that from the visual pattern, to get the figure at stage n, we look back one step to n minus 1 and add on 2. So the recurrence relation for the sequence would be a sub n is equal to a sub n minus 1 plus 2. Since we go back one step, we need one initial condition, and we can get that from the picture, a1 equals 3. Let's go back to a sequence we saw earlier that was not arithmetic. It had terms 3, 6, 12, 24, 48, and so on. This wasn't arithmetic because it didn't increase by the same amount each time. But you might have noticed that the terms do have some very noticeable behavior. They double each time. So the terms of this sequence increase not by the same amount, but by a common factor. Here's another sequence whose terms change by a common factor: 1, 1/3, 1/9, 1/27, 1 over 81, and so on. The differences between the terms aren't always the same, so this is not an arithmetic sequence. But there is a common multiple between each term, namely each term is obtained by taking the previous one and multiplying by 1/3, or dividing by 3. So each term is 1/3 the size of the one that came before it. Sequences like these, where the terms change by the same factor, are called geometric sequences. You just saw two examples of geometric sequences. Here's another, because the terms are increasing by a factor of 5 each time. Here's one that is not geometric, because the second term is 2 times the first one, but the third term is 3 times the second one. Since that's not the same multiple each time, this is not a geometric sequence. Just as with arithmetic sequences, geometric sequences are fairly simple to represent recursively or in closed form. Look at our first example. Recursively, we just note again that each term is twice the one before it, so the recurrence relation should be a sub n equals 2 times a sub n minus 1, as long as n is bigger than 1. And for the initial condition, just look at the first term of the sequence to see that it's a1 equals 3. Likewise, the second sequence would have an initial condition b1 equals 1, and for n bigger than 1, we'd have bn equals 1/3 times bn minus 1. Closed formulas for geometric sequences are a little harder because they aren't linear functions, but instead what we call exponential functions. The recurrence relation can actually help here. In this sequence, I started with a1 equals 3, and then if I want to go to the nth term, I need to multiply by 2 n minus 1 times. So the formula would be an equals 3 times 2 to the n minus first power. And we can check to see that this is correct with Python or a spreadsheet. Let's review this for a moment. Here are 4 sequences. Pause the video and label each one as arithmetic, geometric, or neither. So only the second sequence is arithmetic because the terms are going up by the same amount, namely 4, each time. Looking at the differences between terms in the other 3 show you that these don't increase by the same amount each time. Likewise, I can tell which one is geometric here by looking at the ratios between the terms. Whenever there's a common ratio, there's a geometric sequence. The 4th sequence here is the only one that is geometric because the terms are increasing not by a constant amount, but by a constant factor, namely they're being multiplied by 1.1 each time. In this video, we learned what arithmetic and geometric sequences are and methods for expressing both as closed formulas and with recursion. Next up, we're going to start a mini-series of videos on taking recurrence relations and figuring out ways to express those as closed formulas. We just saw how this might work in the special cases of arithmetic and geometric sequences, but what if the sequence is neither? Stay tuned.